Alrighty, so we're picking up, I was having some trouble with the GitHub Classroom tool. It keeps timing out on me here, like their website I think is screwing up here. So I can't make the link yet for the final project, but I can give you the final project, we just don't have the GitHub repo for it yet. So we'll talk about that. We just want to finish up our binary search trees. Again, we're doing the basic version of it. There's no balancing happening, so if you put data in a bad order, it'll be in a bad form, and we won't get good performance. But what we should be able to get, right, is logarithmic performance, assuming we get mostly this full structure, which we're punting on, so we'll figure that part out after. The last piece we wanted to do was to be able to remove a particular piece of data here. And again, these are interesting. You can do them as maps as well. You can have a key and a value. So that way you can deal with some associated value coming out of these. Hash maps are going to be a little faster, but we trade off a lot of that extra memory usage versus our tree. And then, right, maps are not sorted, where the binary search tree is a sorted order. So we can get the data back out in a sorted form very quickly without having to go and resort it again. So when we remove an item, we want to see, we have to go find where it is. So we're going to go find the node, or find that piece of data first. So we'll have to have it define like a private remove function that has the data and a current node. And we're just going to start with remove given the data and the root, self.root. So we'll start at the top. And then we can start checking less than, greater than, or equal to. Right? So as soon as we find an equal to, we can start doing the remove. So if my data is equal to the node.data, then I want to start doing the remove piece here. Remove and swap. Next, largest, smaller child. Otherwise, right, we'll come back to that in a minute. If we can say, hey, if the data is less than node.data. Now, if we're less than and we have a left child, there's something to do. So then, really, if we're less than node.data and, I guess we'll just, so if we're less than, then we can say if my node.left child is not none, or maybe if it is none, we'll raise a value error, not found. Right? You can't remove it because if you're less than and you don't have a left child, there is nothing less than this value here in the tree. So we can't do it. If you didn't do that, then we're just going to recurse. We're going to call self.remove again, given the data and our node.left child. Right? Because now we found something here. Right? Not found. Now the other option, if we want to save a little bit of checking here, right? Because this is slightly redundant here. Now our else, right, is going to be if my node.rightChild is not none, or is none, right? Then we can raise the value error not found. Otherwise, then we can say self.remove given the data and the node.rightChild. Right? We have to do this check twice, and it feels a little bad. So what we could do if we wanted to, we could just do the check here. We can say, hey, if node is none, raise a value error and say not found. Right? So if we pass in a none node here, we're just done. So all we have to do is just automatically start recursing here. We don't need to do any checks in this portion because we'll raise the value error.
You're removing data? Or
yeah, we want to remove the data from our search tree.
And then will it be replaced by node.data?
We're going to replace it with the next largest smaller child. So because we want to keep ourselves in that tree structure. So we need to find which item are we going to replace ourselves with. Yeah, the next smallest. But if we're not, if I give you a node that doesn't exist because you didn't have a left child or you didn't have a right child, we can just raise this value and say, hey, we didn't find it. And this also is nice because it'll check for that first case. If you try and remove something on an empty, we never check to see if self-root was none or not, right? Because maybe we were an empty tree because you removed a bunch of stuff, or I don't know. So it helps check. It's a little bit cleaner to do it here, right, rather than all the other checks. Right? We could do the same similar thing. If the node is none, we're just going to return false. This saves us a little bit of time. We can say, hey, if node is none, return false. And then I don't need to check in each of these here. Right? It saves me a little bit of typing. That's all. And then I guess we should probably return here, right? Return. I don't know what we're going to return. Maybe we'll just return true. Not entirely sure. Maybe so to remove then, right? We need to find the next smallest piece of data. So our next largest smaller node is going to be node.left. Okay, so if we found it, now we want to start removing it. So let's draw another little picture here. We get back into our form. We have like a 7, and then had maybe a 4, and that had 5 and a 3, and this was an 11 and a 9 or something. So if we wanted to remove 4, and we're going to find the next smallest, or the next biggest smaller child. So we go to the left and find the thing that's farthest right.
So we replace 4 with 5, right?
Well, we don't want to replace it with the 5 because we always want to go to our smaller child. That's just the rule we're going to follow. Yeah. Yeah, so if we don't have a left child, then we can replace ourselves with the right child. So there's a couple different cases we have to look at. So if our node left is none, then we can replace it with the right. So this is the left child. So if the next largest smaller node is none, then we want to swap out with our right child. So we can replace our node. So then I guess we have to see if that one's none as well, right? So if the node.right child is none, then there's nothing to swap, right? If we don't have a child, so if we don't have any children, it's just pretty quick. We can go swap out. So we'll say our node.parent, node.parent. Oh no, we have to find which were we the left or the right child of our parent as well, right? So we need to remove ourselves from that link. So we need to check and see. So we'll say our parent is our node parent, and if node is the parent left child, then the parent.left child is none. If we're not the left child, we have to be the right child. So we'll say our parent.right child is none. Okay, so this is if we don't have a left and a right. It goes pretty quick. If we do have a right, but we didn't have a left, right? If we didn't have a left, but we do have a right, we're just going to swap ourselves for that right child. Yep. So we'll take our node.parent. I guess we still have to do the same check here. Goodness gracious. So our parent, and then we're not going to set it to none. We're going to set it to node.right child. Right. Just goes and checks. Now this is a little bit silly to have the same code more than once, right? So it'd be nice if we had a replace node or something, so we can have a little function here. I don't know, swap node, given a node and node to swap, right? Because both times we go to the parent and we change that one, right? So we'll go to the parent node, then is the node.parent, and if the parent.left child is the node, then we'll swap with that one. So the parent.left child equals the node to swap, and then the node to swap dot parent, node to swap parent equals the parent. Right. Connect those two dots, and really this will happen in either case, I guess. So that's else. So if we're not the left child, we have to be the right child. Swap with the node to swap, and then set that new node's parent in here. So we can quickly swap out the node regardless then. So if the right child's none, we do the same thing. I guess if it is none, that's if the node to swap is not none, this will help make sure it doesn't crash on us here. Now we can do the same thing. So if the right child is none, or if it's not none, it doesn't matter. We can just call self node to swap with node and right child. Swap out the right child. So if we don't have a left, swap out the right, regardless of if it's none or not. If we did, then right, I need to find the furthest right. So then I'm going to say while my next largest smaller node right child is not none, we'll just keep on swapping here. Equals the right child. We'll just keep on driving down, 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 down. So if I have a right, go to the right. If I have a right, go to the right. If I have a right, go to the right, go to the right, go to the right, as far as it goes. As long as it's not none. As soon as it's none, we stop because we've reached the furthest node. And then we're going to swap that one out. So, so if you have to swap that one, now it's possible, let's see, let's change these numbers here. So if we had a 6 here, and that one had a left child, we've got some issues. But we know it only has a single child left. So before we go and remove it, right, we need to put the 5 in its place.
So if you wanted to remove the 4 from here, you would usually take the second smallest.
Yeah, so we would replace with the 3.
Replace it with the 3. But
Yep.
let's say in place of the 5 with like 1 or 2. Would you replace the 4 with the 1 or 2 or the 3?
Where was there a 1 or a 2?
So in the place of the 5 under the 6, it's a 1 or a 2.
So it can't be, because it's the right of 4, so it has to be bigger than 4.
Oh, it has to be.
Right, so anything bigger than 4 has to be to the right of it. Yeah, so we can't get a 1 or 2 there. The only other value we can have here was a 5. Yep.
5.
Yeah, so like this one, maybe if it was, maybe we have like a 0 and then a 1 and a 2. Right, we could have something like that. So we'll go to the left and go as far right possible and find the 2, or we might even have like a 2 and then a 1. Could have something like that. We could have these crazy looking structures here. Then we go to the left and then go as far right as possible. And then we're going to start swapping out. So to swap out the 2, I know I don't have a right child, so I can just put the left child in my place. Then I can put the value back where this one was. Right? So all I need to do is replace the value. So I'm going to swap nodes. So I'm going to keep the value. So I'll have the value will be the next largest smaller node dot data. And then I'm going to swap self.swap nodes. I'm going to swap the next largest smaller node. I'm going to swap that one with its child, its left child, next largest smaller node, left child. And it might be none. Right? That's okay if it's none, because we just want to put that node in its place. And if it's none, it's none. That's okay. We'll go and change its parent, right? Link its parent up with this one. Then I can take this value, and I'm going to put the value in place of my node. I can say my node.data is equal to the value, because that way I keep all my other connections in place here, right? I don't have to delete any of my connections here. I can just say, hey, let me take the 2, right? I put the 1 in its place here. Swap that one out, and I'm going to put the 2 back here. Now I'm still in a tree, but in a search tree form, because everything bigger than me is to the right, everything smaller than me is to the left. We keep our form here. So the only node that gets replaced is at the bottom of where we found it. Here, and we just swap up the data. It's sort of a quick way for us to go quick-ish, right? This should still be logarithmic, assuming we're in a mostly full form, right? That we don't have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like in a big chain here like that. Then we'd have some trouble. But this is, assuming we're mostly in this, it works out pretty well. Yes, we just keep on recursing until we find that data, and then we can swap it out with the next largest smaller node, right? And go and find those and find those and find those. So we should be able to remove values. Then the last thing we want to do is something like to print things in order. I don't know, print in order. It'd be nice if we could do some sort of iterator, but this is probably fine for now. We're going to do left, myself, and right, because we always want to go to the smallest first, because we can get ourselves in order. So this, again, we'll just have a helper function. So we'll define print in order given self and a node, right? And all this one needs to do is call self print in order given self.root as the node. Right? I don't want someone to have to pass me a node. They don't know about the node class. That's a detail we're hiding, we're encapsulating in, right? So the function that we give them is just print in order, and we'll go do the thing. So to print in order, we're going to say if node.left child, right? And that's really if it's not none. If it's there, we'll call self.print in order given the node.left child, and then we'll print node.data, and then if my node.right child, self.print in order given the node.right child.
So it's recursive, right?
Yep. Yeah, so it'll keep on recursing all the way left until it finds the smallest node, print it, and then go back to where it was called, print that one, and go right. So that way it follows this order, right? So we're going to go all the way left. We have no more left, so we'll do the 0, and then we'll go to the right and repeat. And we get a 1. There's no other children. We go back. Now we're back at 2. We print the 2. We go to the right. This one says go all the way left first. Now we get the 5. We get the 6. We come back. We did all the left. Now we do 7. And we go to the right. We go all the way left. We get the 9. We get the 11. So it should print it in order. So I should be able to take our binary search tree. I don't know, values as a binary search tree. I don't know, what do we say, 7, and then values.add, or what do we call this one? Insert. That's a weird, I probably should have just called it add, but whatever. So what do we have in here? We had 2, a 6, 5, 6, 5, 0, and a 1, and an 11, and a 9. So print in order. So it should be able to print all these out then in order. See if it works. It might crash. Oh, shoot. Okay. Yeah, I meant self._root. Thank you. Private root. 0, 1, 2, 3, 5, 6, 7, 9, 11. That actually worked. I'm kind of amazed. Usually doesn't work the first time. But
how does so can you go up to the code of the technologies? So if you know the left child and then if you know the right child, and then if you go to them, can you open the tree? Yeah. So it goes all the way left, and then if it doesn't find another left, it goes right, and then goes back up. Right?
So before it goes to the right, it prints itself.
Yeah.
Yep. And then it will check to see if there's a right to recurse.
So, and then how does it because then after it prints the right, it goes back up to the one before. So how does it automatically go back to the one above before? Because it's not in the code to go back.
Or so it's because we were relying on recursion. So we said, hey, we're going to print starting at 7. The first thing this does is say, okay, we're going to print at 7's left child, which is 2. Right? The first thing that one does then says, okay, we're going to print the left child, which is we're going to print at 0. There is no left child, so we print out the 0. Right? The next thing the step does is say go to the right. So now we're printing at 1. It has no left, so it prints itself. It has no right. This comes off the call stack. Now we're back at print at 0. We already did the right. We're done. It comes off the call stack. Now we're at 2. We did left. Now we're going to print ourself. And the next thing it does is go to the right. So now we're going to print at 6. The first thing 6 does is go to the left. We say, okay, now we're going to print at 5. 5 says, okay, I don't have a left, so I can print myself. We get the 5. And it doesn't have a right, so this comes off the call stack. Right? So it's relying on the recursion piece to keep, it remembers where it was. Yeah?
Essentially, what is the difference between a sorted binary tree and the priority queue?
So the priority queue is keeping itself in that full structure, so everything gets shifted, one level at a time all the way to the left. It fills up that way. And then only the top node is the smallest, right, for a minimum priority queue. It doesn't keep it in a sorted order. It keeps it in I'm the smallest at the top order, and I'm never bigger than my children. Where with the binary search tree, we're very specific around where it is. So we get logarithmic performance for adding stuff, but you can't traverse a priority queue without destroying it. Right? Because every time you take a node off, you have to go and then reheap, or upheap or downheap the values. Where with the binary search tree, I'm in a fully sorted form, so I can get all my values out without destroying the tree. So if you're going to keep the values around, the binary search tree is useful. So you can read it, do something with it, add stuff to it, change it, read it again. It keeps it. Where the heap or the priority queue, if you want it in that sorted order, you have to delete the whole thing essentially, and then if you want to put it back, you have to put it all back in again. So it's going to be less efficient for you.
Thank you.
All right, awesome. So I think that was about it for our trees, the binary search tree. I can't get this GitHub Classroom thing to work. It's like freaking out on me here. I don't know if we're getting timed out, or Nginx is a load balancer tool. So I don't know what's happening with their site. I might try it again later. It's been all morning now. But we can talk about the final project. I just won't have the GitHub repository for you, unfortunately. So let me do that. Does that sound good?
Is it going to be on poker or
Blackjack.
Blackjack?
Yeah. So let's do a new, does it need to be a new group? I think it needs to be a new group. So this is final project. And we can add one here. So final project. And then this should be due, let's see if I did this right here. I gotta check the final exam schedule one more time. Your board, final exam schedule. So because we meet Tuesdays at 2, so we should be.
To go, right?
I'm sorry?
We still have topics to go, right?
Yeah, a couple more. Yep. So we should meet at code G, right? We're Tuesdays at 2. So G puts us at Tuesday the 23rd at 3 p.m., right? Tuesday the 23rd, 3 to 6. So this will be due Tuesday the 23rd, 3 p.m. So I'll get you that GitHub link in a minute. GitHub link TBD. And then I'm going to go steal this from my other class here. Give me just a second to copy paste. It worked earlier because I got the link for them, so it worked this morning. It's crazy.
And the range from 0 to 10, how hard would you say this one is?
It's long, but not crazy hard. No, I mean,
Doable.
7 or 8. Yeah, it's doable. It's not impossible for sure. It's going to take a little while here.
So how long do you think it would take?
I'm sorry?
How long do you think it would take to do?
So we're doing it in 3 parts, essentially.
Like you need 3 classes? Is that what you mean by 3 parts?
No. So there's like 3 different things we're doing, essentially. And so, yeah. Sorry, give me one second. I didn't have my rubric. That's why. Okay. Why didn't I not have the rubric in here? That's fine. We'll do that after. All right, and this is URL. I'll add the rubric in a second. All right, so we're going to build a blackjack simulator. Now, I think we actually have to work in pairs, right? I don't know how this got out of sync with the other class. We're supposed to have like the same outcomes. But I thought one of our outcomes was working in pairs. Yeah, as part of a team. Okay, so I don't know why that wasn't. So we will be working in pairs for this one here. Please let me know what your partner is. Partnet is. You can set up shared access to a repository. All right, so we're going to build a blackjack odds calculator, but it will also play the game. So we're going to do 2 pieces. So part 1 is we're going to write some classes that act and do all the blackjack logic. So when you play blackjack, generally we use a bunch of decks. So 6 to 8. We'll just say 6. It's pretty easy. So you put them all together, shuffled up. You call it a shoe. I don't know why.
Yeah, that's what I'm going to ask. What's a shoe in 6 decks?
Yeah, so the shoe is like the big thing all the decks go into. I think that's what it's called.
And 6 decks together, you just shuffle them all.
Yeah, shuffled up, yep. And then when the shoe gets to say less than 100 cards or so, you want to reshuffle them all together again. Shuffle them all back up. So as you play blackjack, you have your 6 decks of cards, you play. When you start getting low on cards, they'll shuffle them all back together again. They don't shuffle every time like you do in poker. That's how they play. And that's one of the reasons if you start counting cards, you can get slightly better odds in your favor, that sort of thing. But then casinos don't want you to do that because then you can make money off of them, and they don't want people making money.
No, I'm sorry, I did not get like the shifting system.
So when that big stack of 6 times 52, 312 cards, gets down to less than 100, we're going to shuffle 6 decks back together again and start back up with 312 cards again.
So you got all the cards together and should reshuffle.
Yeah. So you play with this 6 set of cards, and you don't shuffle until you get to this point. That way, we're not going to count cards, but you could. That's a fun thing to do later. If you count how many of each kind of card come out, you can predict, what's more likely to show up. There's all sorts of interesting strategies around that you're not supposed to do at casinos. But just setting up all the classes here. So ways that I'm going to interact with these things, right? This shoe should just give me a card every time I ask for a card. It should take care of the shuffling for me, right? When we think about how we want to design our classes, and I don't want to have a separate step that says, hey, I want to go shuffle this thing. I could, but it's probably easier if the class just does it for me. So I could just say, give me a card infinitely, and it'll always give me a random card. at some point it'll reshuffle itself, right? I don't need to know those details. I might have ways of tracking hands. All sorts of things we can have in here. We're designing a blackjack game. Part 2 is taking those classes and hooking them up with user input, so letting someone play it manually. Say, hey, I want to play blackjack. It's just one person versus the dealer for now. And blackjack is a game, it's 21, some other people call it, so you have to get up to 21 points without going over, or really you want to beat the dealer. So the player first, and then what you have to do is have a higher number than the dealer, but if you go over 21, you lose automatically. That's why casinos like blackjack, because players can lose without the dealer doing a single thing. So when we play, we get 2 cards and the dealer gets 1. So we see what the dealer has for their 1 card. Now we know, because there are 13 face cards, right, 2 through ace, I'm going all the way up. Now jacks, queens, and kings all count as 10 in blackjack. So there's 4 out of 13 cards that have a value of 10. So 4 out of 13 is close to about a third, close-ish. So a third of the cards, a third of the time when he gets another card, he'll have 19. Yeah.
And the ace can either be 1 or 11?
Yes, yeah, aces they'll be 11 until you go over 21, and then you want to change their value back to 1, so you're not over 21. Yeah, so the or is really just always counted as 11 unless you're over 21. Then you want to count it as a 1.
Okay.
Yep. So we see we have a total of 7. Definitely we can take another card. So the 2 options we're going to deal with are you can stand, which means I'm going to stop taking cards and just see if I win or lose, or I can hit and take another card. So I'm going to take another card. I'm going to hit, I get another card. Now I have a total of 15. I could stand or I could hit. Now for our purposes, we'll just say stand. Let's see what happens.
What is stand?
So stand means I stop taking cards. Yep, so when you stop taking cards, then it becomes the dealer's turn. Now, the dealer will always take another card until they get to 17 or higher. That's the dealer's rule. So no matter what happens, when the dealer has 16 or less, they'll take another card over and over and over until they get to 17 or higher. If they get to 17, 18, 19, 20, or 21, then we see who has a better hand. If they go over 21, we win. Right?
They need to be at least over 17.
17, 18, 19, 20, 21, they will stop. If they get over that, then they lose and you win. But what happens is, if you go over 21 first, they automatically win without taking another card. This is why casinos like the game, because players can just lose automatically. It doesn't matter what happens to the dealer. So that's their advantage, because you have to go first.
Basically, the first one to play is more likely to lose, right?
Yes, yeah, and the dealer always goes last. Yep, so this is why you don't ever play with people, right? You play against that. So starting at 21, we've won, essentially. We can't lose. If you tie, if you both end up at the same number, then you just get your money back. You didn't win any money, but you didn't lose any money. So we'll call that a draw. So you can win, you can lose, or you can draw.
But do you always know each other's hands?
So the players, we're just going to play one player and one dealer.
Okay.
Right? In the real world in blackjack, there can be like 10 to 12 players at a table at a time, all playing against the dealer at the same time. So players don't play against other players like poker. Everyone plays against the dealer.
No, I'm sorry. My question was, does the player know the dealer's hand?
We see one card.
One card.
Yep, we see one card. Yep.
But if you stand, so you stop drawing new cards, are you still seeing
Yep.
the cards?
Then you see what cards they get. Yep. So they got to 20, they stopped, and we won.
Is that exactly like that?
Yeah. Yep. Now, this should let me play the game, right? So then I get to see how much did I win, how much did I lose, that sort of thing. That's part 2. So part 1 is setting up the classes. Part 2 is building it out with input to let the user pick. Do you want to hit or do you want to stand? We're just going to assume they bet $1 every time. So if you win, you get $2. If you lose, you lost your $1. Right? If you tie, you get $1 back, which means you've net gain of nothing.
So for every single win, we get on 2, and for every single loss, you lose 2.
So you pay the $1 to play the hand.
Okay.
If you win, you get 2 back, so you've gained $1. If you lose, you lost your $1. If you tie, you get your $1 back. You've lost nothing.
So that's regardless of the number of cards you have drawn.
Yeah, for our purposes. So in the real game, you can bet different amounts. You can say, hey, on this hand, I want to bet $100. On this hand, I want to bet $1. We're not going to bother with that because that's trickier.
Okay.
That's another strategy you can do to win more money. But that's part 2. So part 3 is going to simulate. So using these classes, we need to be able to automate the process of betting, hitting or standing. And what we want to do is we want to see what is going to lose the least. You're never going to win, right? We always lose money at blackjack. because it's a casino game, but what it will lose the least. And we're going to build out a strategy. We're going to show the data. So what we want to do is then for every hand value that we start with and every card the dealer starts with, we're going to build out this table. So if you look at the Wikipedia article for blackjack, blackjack odds on Wikipedia. Nope, not that one. I just want the Wikipedia article. Where did I do? Here we go. There's a basic strategy to it, and this is all based on the odds. So this just tells you what you should do. You should say, hey, if the dealer has a 2 and you have 18, 19, 20, or 21, you should just stand. Don't take more cards, because you will probably lose very quickly. Right? That, I think, makes a lot of sense. But now if the dealer has a 2 and you have a 13 or 14, the odds say you should just stop, because the dealer will probably bust more often than not. Now, you could take a card, right? If you have 13 and you get a 10, you're going to go up to 21. That's good. But if the dealer has a 2, you should just stop. So this is telling you what should happen, but it doesn't give us any of the probabilities, any of the odds. So what we're going to do is we're going to find those numbers by actually just playing 100,000 times. So for every one of our starting hand values and for every one of the dealer's hand values, starting card values, we can have results. We're going to see how many times do we win, how many times do we lose, how many times do we draw, based on what did we do. So whether or not you should hit or stand, don't worry about the DH, that's just a hit, and H is a hit, US is a stand. We're not going to do any of the, there's other fancy things you can do with blackjack that are just not worth it for us. There's also, if you have pairs, we're not going to deal with pairs. You can split, we're not going to deal with splitting. Right? We're not going to split, we're not going to double, it's fine.
So what exactly is part 3?
So we're going to run this a bunch of times. So we're going to, for 100,000 times, start a game, start a round, and then we'll randomly pick hit or stand. So, hey, I had 7 total and the dealer had a 9. And then if the game, it will randomly pick hit or stand, and we're going to see, did you win, lose, or draw, and we're going to track those results. Right? So because there's 18 cards we could have, 18 starting values we could have from 4 up to 21, and then there's 10 values the dealer could have from 2 up to 11. Right? So 18 times 10 is 180. Right? So we have 500,000 times we're doing this, divided by 180 means each time we're going to get about 2,700. Is that 180? Is that right? I guess so. Probably is. 2,700 times that this particular combination would have come up, where I had a 7 total and they had a 9. I had a 14 total and they had a 2. I had a 17 total and they had a 5. Like all those different combinations, the 180 different combinations, will happen a bunch of times because we're doing, 100,000 times. That's why, 100,000 times divided by 180. There we go. This number looks a little more familiar. So about 550 times this should happen. So half of those times we're probably going to hit, and half of those times we're probably going to stand. We just want to randomly pick hit or stand because we don't want the user to have to enter anything. We're going to generate the odds. We're going to just do this a bunch of times to get 250 hands where this started and I hit. 250 hands where this started and I stood. Right? So what we're going to get at the end here is we're going to get this table of showing hit and stand for each starting value. Did we win, did we lose, or did we draw? So you can get the data back out, and if we look at the data, we'll say, hey, when you had 18, 19, 20, 21, you won more often when you stood, and you lost a lot when you hit. So we can look at that and say, okay, the best strategy should be just stand. Stop taking cards. When your total was 18, 19, 20, or when your total was 17. What happened when you hit? What happened when you stood? How often did you win? And so if you gave someone smart who knows math, like you folks, the table, you could generate this sheet for someone else. If you give an average person off the street a table with a bunch of odds and results, like, hey, 27% of the time you win, 37% of the time you lose, and it's like a two-dimensional table like this with 6 values in each one, their eyes are going to cross because they're not numbers people. Yeah.
Okay, so just make sure. So part 3 essentially revolves around creating a system where we will automatically make the system play
100,000 hands. Yep.
And using the table's rules.
Not using the table's rules. So the 100,000 hands, you just randomly pick hit or stand.
Okay. So the only thing that should be printed is like the final result of win, losses, and draws?
The table, yeah. So for my starting value of 4, for the dealer 2, here's win, loss, draw. When I hit, here's win, loss, draw when I stand. When my hand value was 4 and the dealer's value was 3, here's how much win-loss draw for stand, here's win-loss draw for hit. Right, so for each of these pieces here, we've got 6 pieces of data. We've got the stand win-loss draw, and we have the hit win-loss draw for each column, essentially, each intersection here, sorry, each cell. Right, so like if you were to think of this in like Excel, right, because people love Excel, right? So this will be player hand, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh my goodness, I'm embarrassingly bad at Excel. There we go. And then this will be the dealer's hand. 2, 3. Right, so somewhere in here then we'll have, why am I off one? That's fine. So this will be, for win, hit, wins, 10% or something, hit, draws, 2%, I don't know, hit, loss, 1%, I don't know, these should probably add up to 100, sorry, something in here, right? And then we'd also then have the stand wins, some percentage here, 25%, stand draws, really low. Actually, we'll never draw, right? Because if I have 4, the dealer can never have 4. So it'll probably be 0 here, and then stand losses, 2%, I don't know, just some value here. So we're going to have each of those pieces of information for when my hand was 4 and their hand was 2. When my hand was 5 and their hand was 2. When my hand was 6 and their hand was 2. Yeah.
Okay. I think I got it now. So the step 1 is building the classes that will allow us to play the game.
Yep.
So not only should we create the part 3, which is like the automatically part of it, but also we want to be capable of playing it, right?
Yeah.
Okay. So when we're playing, we can either stand or hit, which is draw another card, right?
Yeah.
So if the system automatically hits, it should, like the next round, either hit another or stand, right?
Yeah, so when we do the 100,000 hands, we're just 50% of the time we'll hit, 50% of the time we'll stand, because we want to get a good distribution of what happens.
Okay, and how exactly should we track the best strategy?
Well, so we're not tracking the best strategy yet, we're just generating some data. Right? We're just outputting a table here, so we're not building a strategy yet, we're just going to spit out a bunch of data. Here's the actual results. From this, we could build a strategy, and then we could use that strategy and then program our player to use a strategy. That's another step we haven't got to yet. That would be the next step. Is okay, now let's see if they use a strategy, how well do they do playing 100,000 hands? Right? This, just simulating, is going to lose a lot of money because we're trying to lose. Like, if you're going to tell me how many times you lost when you hit on 21, it's a lot. Actually, on 20, you're going to lose most of the time when you hit. On 21, because you have an ace, you're not going to lose all that often, as much. But like, if you're at 20 and you hit, every card but an ace will make you lose, right? So you'll lose a lot every time you hit, but when you stand, you should win a lot, right? So we can look at that data and say, okay, here's a good strategy as the next step. We're just not there yet. Yeah. So that'd be the next, like, let's analyze the output here and figure out a good strategy, and then let's try it again and see what we get and see if we can tweak it and do all sorts of fun stuff. That's beyond us at this point. Yep. All right, so then for points here, let me do our rubric. This is our final project. We're gonna use this for grade. I really thought I did this already. That's super weird. So this will be part 1, it's 10 points. Part 2 is 10 points. Part 3 is 10 points. And you get 10 points for having 10 git commits or more. So if you only commit one time, you don't get 10 points here. You get 1. You can still pass, but it's not good. So this is your incentive to build it little bit by little bit by little bit by little bit and work on it for the next 3 weeks, right? Encouraging you to do that. And this also makes this hard for someone to use ChatGPT to get an entire solution and give it to me in 10 pieces. And if they do, that's really obvious, actually, that they've like split it into 10 pieces, because it doesn't look like when you write code and make changes and write code and make changes and write code and make changes, you can usually tell. Right? Points just for working on it incrementally here, even if it doesn't even work. That's okay. But it's more than like, you can't just change one line and call it. Like maybe a substantial commit, git substantial commit. Right, so we're going to do this over the next couple weeks, work on it here. If we look at our schedule here, we're going to have some extra time, right? We don't do super deep on sorting and selection. So we'll be able to take care of most of it on Tuesday, I think. We'll have a little extra time Tuesday. The lab should be pretty quick on Tuesday, so you have some lab time to work on it as well. And then Thursday, again, whatever little bit we missed, work on the project. When we talk about ethics, that should probably only take the Tuesday. We'll probably have all of Thursday to work on it. And then all of 416 and 418, I have no plans to do anything new. There will be a really short ethics lab we can get into on 416. It should only take like 20 minutes. And the rest of that lab time we can also have for final project time. And then we'll do presentations a month from now. So ideally we can get it done by the 18th, and you can actually focus on your other finals for other things here. If not, that's okay. We've got some time, but putting it up to the 18th gives us 1, 2, 3 weeks, right, to get it done. Then we've got the last couple days, last weekend, before you have to present. When you present, you'll just go and run it. You'll play blackjack. Hey, here's here's part 2. Here's how you can play it. We'll play a couple hands. And then here's part 3. It runs it and spits out the table result. So that's about all it is for it. So doing this sort of simulation is fun when we're trying to model things in the real world, because figuring this out mathematically is doable for blackjack. Right? It is mathematically solvable. It's just harder when you get into more complex problems. You can't always even find the math for it. So just simulating it and doing it a bunch of times and getting some results back out is super useful. And that's one of the things I like doing. All right, questions, thoughts, concerns? Okay, I will get that GitHub link working at some point. I don't know why it's not working. I might try it on my phone Wi-Fi maybe. I wonder if they're just blocking our network. So we'll see. I can always set up other repositories if I need to. So let me know, and we can go from there. Okay? Awesome.
Thank you, sir.